So parity checking is just a technique for identifying whether or not there's an error in a binary signal, and more specifically, and kind of at its core, is just whether or not there's been an electrical interference or some other kind of interference or error that has resulted in zeros being flipped to ones, ones being flipped to zeros, and that kind of thing. And so there's lots of different ways you can do a parity check, but I'm going to demonstrate a really simple way of doing a parity check. So parity just refers to the evenness or oddness of a number. So for example, 128 is an even number, it's got even parity. 127, odd parity. In binary, 12 has a even parity, and 13 has an odd parity. And you can tell the difference between an even and odd number in binary pretty simply. Just the last bit, last number being a 1 or a 0. So 1 being even because it represents the powers of 1, or the 1 multiples of 1 in the powers of 2, as binary goes, that column, and then 0, a 0. So, yeah. And so a parity check is basically this here will be a simple parity check that I'm doing now. So I want to look at this 7-bit sequence. So a 7-bit sequence is good because you can easily turn it into a byte, and a byte is kind of a standard size. But so you sacrifice 1 bit of data for an entire to ensure that the parity is being met properly. And so if we do an even parity check, you can do an even or an odd parity check, and they're kind of just the opposite of each other. But once you learn one, you just know to invert one to get to the other. So let's do it. I'm going to do an even parity check. So in this 7-bit number, you just want to count the ones. So there's 1, 2, 3. There's 3 ones here. So what that means is that if we're doing an even parity check, we want there to be an even amount of numbers, ones, even amount of ones. So what I'll do here for the parity bit, I'll chuck in a 1. So now that they're now in this byte, I've turned this 7-bit sequence into a byte, and there are an even amount of ones in here. Similarly, for the next one, 1, 2, 3, 3 ones here, so add 1. And so the byte kind of becomes this kind of thing. And the reason you want to do that is because when whatever is reading or receiving this signal gets to the start of the byte, it'll see a 1 at the start, and it'll say, okay, if there's a 1 at the start of this byte, then that means that there are an even amount of ones in this byte. And so it'll check, there's 1, 2, 3, 4, yep, even amount of bytes, and so nothing is wrong. Or there could be something wrong, but nothing obvious and as blatant as that is wrong. And same for here. In these two cases, you'll notice that there's already an even amount of ones in the 7-bit sequence. So you just put a 0 on the front, and it remains. So if it sees a 0 at the front, it'll say, okay, it's an even amount. Well, actually, for all bytes, it'll say there'll be an even amount of ones. But yeah, it's kind of, if you have it at the start, you can say, if there's a 0 here and 2 here, it's fine. But if there's a 1 here and a certain amount in here, then something might have gone wrong. And so longitudinal is just a kind of layer on top of that, where you are checking the parity of this direction. So say you want to have a longitudinal check of these 4 bytes. So what you would do is you would go down this number, this number, this number, this number, and then if there's an even amount, you want to create an even amount of bits in that row. So 1 here, so that now there are 2, so this will be the longitudinal row. And then there's 2 here, so it'll be a 0, and then 0, 1, 0, 1, so there'll be a 0 here, 0, 0, 1, 1, 0 here. I just realized I think I'm a row ahead, so this will be a 1 and then that will be a 0 to create an even amount of 1s in this column. And then there's already an even amount here, and then there's already an even amount here, 0. So what you can kind of see here is with an extra byte. So with an extra byte, you can check the last 4 bytes, and with that, you can kind of narrow down exactly where the problem is once you add longitudinal checks to it. Because if you notice that there's an error in this byte, and that, say this one doesn't match up, then you know that this bit here is the culprit and it's wrong. It's just a way of this is a good way of visualizing it because it's kind of makes it like a matrix or a graph or a table, and so you can kind of see exactly which is the problem bit. But obviously, if you're transmitting this, it would be something like this, less than 0. Yeah, so you'd kind of get like this. So the parity checks are here at the start of all the bits, and then this one here. And so this kind of checks itself to see if 1 or 0 has been flipped. And so yeah, that's pretty much, and then an odd parity check would literally be the inverse of that. So you want to change all these parity bits to the opposite of what they were, and this would be a 0, 1, 1, 0, 1, 1, 1. 1? How many did I get the wrong amount of bits there? You know, I don't think I had the right amount of bits there. Oh, I wouldn't have, because I only had so many bits beforehand. But yeah, so it's a way that you can structure your signal in order to be self-checking. And yeah, it's an incredibly useful low level. Yeah, so